Right now, you are within arm's reach of a dozen computers, not laptops, tiny ones hidden inside the things around you, and most of them are nothing like the chip in your phone. Let me show you the difference. Think about your morning. The microwave, the car that started, the remote, the washing machine, the key fob in your pocket. Every one of them has a small computer inside, quietly doing its job. We build tens of billions of these every year, far more than all the laptop and phone processors combined. So here is the question. Why is a chip worth a few cents enough to run your microwave when your laptop needs one that costs hundreds? The answer is that these are two different kinds of chip. To see the difference, strip any computer down to the bare minimum. You always find the same four parts. A processor to actually do the computing, memory to hold the program, which is the list of instructions, memory to hold the data it works on, and some way to reach the outside world, to read inputs and control outputs. Four parts tied together by a bus. Hold on to these, because the whole story is about where they live. A microprocessor is just that first part, only the processor. Open it up, and it is endlessly fetching an instruction, decoding what it means, and executing it billions of times a second. But notice what it does not have: no program of its own, nowhere to keep its data, no way to touch the outside world. It is a brain in a jar, powerful, but with empty sockets all around it, waiting to be wired up. So to make it useful, you build a whole system around it. On a circuit board, you wire the processor to memory chips for gigabytes of fast data, to storage that holds the programs and the operating system, to a crystal that keeps time, and to chips that handle input and output. That board, the brain plus its supporting cast, is your laptop. It is your phone. Huge capability, but it takes a lot of parts to get there. Now for the other approach. Take those exact same four parts, and instead of spreading them across a board, print them all onto one piece of silicon. The processor, the program memory, the data memory, and the input and output fused into a single chip. That is a microcontroller. One component you solder down, and it boots up and runs your program entirely on its own. A complete computer about the size of a fingernail. And here is what makes microcontrollers special. Built right into the chip is a whole ring of peripherals, pins it can switch on and off, a converter that reads the voltage from a sensor, timers that measure and generate precise pulses, and serial buses to swap data with other chips. This is how one tiny chip can read a temperature, blink a light, drive a motor, and talk to its neighbors, all with almost nothing wired around it. That all-in-one design forces a trade, and you can see it in the memory. A microprocessor expects gigabytes of external memory, and it loads a big operating system from storage before it can really get going. A microcontroller carries its memory on board. Often just a couple hundred kilobytes of flash for the program and tens of kilobytes for working data. Drawn to scale, the microcontroller's memory is a sliver, tens of thousands of times smaller. But it runs the instant power arrives. No disk, no waiting. Speed splits them too. A microprocessor runs at gigahertz, billions of cycles every second, with several cores, large caches, and deep pipelines that let it do many things at once. And remember, 1 gigahertz is 1,000 megahertz. A microcontroller usually runs in the megahertz with a single, simple core that does one thing at a time. On paper, that sounds far weaker, but the simplicity is the whole point. It makes the chip cheap, tiny, and above all, predictable. And predictable timing matters more than you might think. A microprocessor runs a big operating system that is always juggling tasks, so the time it takes to react to an event wanders, and once in a while it is late. A microcontroller runs with little or no operating system, so it can guarantee a response inside a fixed deadline every single time. When a car senses a crash, the airbag has to fire within milliseconds, with no excuses. That is a job you hand to a microcontroller. Then there is power and price. A microprocessor can draw tens of watts, enough that it needs a fan and a heatsink just to stay cool, and it costs tens to hundreds of dollars. A microcontroller sips microwatts to milliwatts. It can run for years on a single coin cell, and it can cost less than $1, thousands of times less power, for a tiny fraction of the price. That is exactly why there is one inside your remote and not a laptop chip. Now, the truth is that this is not a hard wall. It is a spectrum. Lean one way, when you need low power, low cost, and tight timing, and you want a microcontroller. Lean the other way, when you need raw performance, lots of memory, and a full operating system, and you want a microprocessor. And in the middle sit the systems on a chip, the powerful processors inside your phone or a Raspberry Pi that blend a strong brain with built-in peripherals. So how do you actually choose? Reach for a microcontroller when the job is a single dedicated task, when it has to react in real time, when it runs on a battery, when it must be cheap in huge numbers, or when it talks straight to hardware. Reach for a microprocessor when you need heavy general computing, an operating system running many apps, plenty of memory or rich graphics and networking, and when raw performance matters more than saving power. So that is the difference. A microprocessor is a powerful brain that needs a body of memory and chips around it. A microcontroller is an entire little computer on a single chip, built to sense, decide, and act all on its own. Both are absolutely everywhere. They just quietly solve very different problems. And now you will know which is which.